We're letting robots out of the cage. Danger, danger. In this episode, you'll learn different techniques to keep robots and people safe. So, why are we letting robots out of the cage? Or what does this actually mean? Ian, can you help us understand this?
Sure. Really traditionally in factory automation, robots are literally in cages to keep them separated from humans. And that's a very structured environment. Even in warehousing, they often are behind a barricade and kept separate. What's happening is with the rise of robotics, you're talking about everything from delivery drones that are flying in through the warehouse bay doors to uh, the equipment carrying pallets that are trying to go outside of their previous cage and be amongst humans and go to the loading dock or even go out to trucks and be part of the loading solution. So it's becoming critical to make sure that your your robot is aware of its surroundings.
And what kind of obstacles can be in the way for robots as they get outside of the cage?
Yeah, I mean, things you might not have thought about. If you're heading to the warehouse loading bay door, is there a stairway you might fall down? Is there a is there a forklift that might come into play that you weren't expecting and knock off the load that's on top of your robot? There's all sorts of unknown hazards, and I think the important thing is for the robot to have the autonomy to be able to manage those hazards on its own.
And most importantly, there's humans that could be the hazards.
Of course, yeah.
Yeah, so these are really great examples to understand why robots are starting to go outside of the cage and then the problems that presents. So, Altaf, I'd like to get your insights on what are the different techniques and ways that robotics developers can institute or architect around to prevent or protect against these obstacles.
Right. So the key here is really robots having an awareness or a perception of its environment that it's operating in, being able to detect other robots, other objects, people surrounding that area and be able to avoid them. So this requires multiple different types of sensors. You need vision, LiDAR, radar, doing sensor fusion across those. So not only can you see and recognize the objects that you see, but also where they are, how far they are, if they're traveling towards you or away from you, so you can make those safety decisions. And like Ian mentioned, there are other hazards there. If there's stairs or whatever, you want to make sure that you have some of the intelligence in the sensors to be able to make decisions that if you're going to fall off a stair or fall off a cliff, you want to be the sensor to be able to stop the robot and not have to wait for any delays for the central brain to make those types of decisions. So ideally, you want to have a distributed safety architecture. That would probably be ideal. In most cases, customers do implement more of a centralized architecture, but in this case, adding more intelligence at the edge may be a better solution to solve these problems.
Yeah, especially because there might be some known hazards like a staircase or a loading dock, but there's no way you can plan against all the unknowns.
Yeah, exactly. So if you have other robots that are navigating in that same environment, you need to be able to navigate around those. If there's other obstacles in your way, you need to be able to navigate around those as well. And also to avoid people. So being able to detect the speed of other objects, be able to detect people, and depending on how far away you are, adjusting your speed and even stopping depending on the actions that you need to take.
The other aspect of this is that, you know, there's the sensing itself, but then there's also the concept of having supervisory control over the main function of the vehicle, of the robot. So, if all of a sudden calculations within the robot say go faster than you really ever should go, there should be a supervisory processor there that's saying, no, you can't. I'm not letting you go faster than this speed, or I'm not letting you go outside these boundaries. There's a lot of importance to put these fail-safe mechanisms between what the robot thinks it should do and what it's actually should be allowed to do.
It's like an ecosystem where you're really looking at different, what you called,
Well, it's a supervisory controller, safety controller, in addition to the main processing that's going on in the vehicle. Yeah.
okay.
Yeah. Yeah, I think what Ian's mentioning, if something goes wrong with the software that's operating on the robot, right? So it calculates some speed that's way out of bound of what it's supposed to be operating in as a safe limit in that environment. You want some safety mechanism to detect that and say, no, you can't go faster than X. That's the limiting speed.
Checks and balances.
Right. Yeah.
So bringing intelligence at the edge, but also being aware that there's some danger zones and having a function that's
Right.
able to.
Yeah, checks and balances, basically.
Yeah.
Right.
It's analogous to the idea if you go and touch a rose, right? It's a thorny rose, and your fingers know that you've touched it, and they'll stop you
Right.
before your brain even has a chance to process it. So build that same sort of sensory system in that has, the capability of giving you senses, but also reactions that are over and above what your brain is asking it to do.
So can you, Ian, talk about some of the NXP technologies that can be used to provide these sensing capabilities and this intelligence at the edge?
Sure, there's a lot of new technologies that can help you with localization. Ultra wideband's a great example, but also we're developing Bluetooth channel sounding, and that helps you with position and localization in an environment like a factory environment. There's some other neat, interesting use cases. For example, like, I don't know, precision docking with a charging station is a great use for point-to-point ultra wideband. And of course, we have parts like analog front ends that can take in all kinds of other types of analog sensors, and of course distribute them throughout the architecture of the robot. Our parts like MCXN have both the local processing, local decision making, and the network interfaces that might be required in modern robotics architectures.
So robots are getting smarter. They're extending the range of what they're able to do and where they're able to go. And all of this creates the need for developers to dig into these different technologies and architect what works best for their use case, from sensing and intelligence. And I think you talked a little bit about connectivity and other robot examples. So I would assume that that also applies here, how the robot fits into the overall system. So we've talked a lot about these different types of sensing technologies, and I think the context that it's been done in is about how to sense other robots or other objects that are in the path of the robot. But what about humans? Because we also talked about keeping humans safe. So are these the same technologies to keep humans safe, or are there different ways to do it?
Right. I mean, humans are the most valuable asset in a company. So we want to make sure the human is kept safe at all costs. And so that could involve both these active and passive sensing technologies. So if you think of, vision looking and trying to identify a human, or the sensor fusion where you vision and radar, but you might also include something like a active tag that has to be sensed or not sensed, and be either Bluetooth, ultra wideband, or other technology that says, I am in proximity to a robot, and the robot knows that, or it expects it, and it reacts and stops its activity when you get too close to it. So there's multiple, depending on the type of environment, that can be super critical to include those types of technologies. The other interesting thing that's being investigated is using parts like our Bluetooth or ultra wideband parts as small little radar-like sensors. So not just the point-to-point connection and the distance measurements, but also can it operate as a human sensor, whether that's using radar type ideas.
Thanks, guys. For more conversations at the edge, click on the links below.